Hi everyone, my topic is BESIII check bounding algorithm based on H classification GN. So today I'm going to talk about for BESIII, we build a pattern map based on Monte Carlo simulation and talk about graph construction method, H classification, check building, and show their performance. The BEPC2 is an electron-positron collider located at Beijing, which is a high luminosity multi-bunch collider ring in tau charm region. The BESIII detector BEPC2 is designed to study the electroweak and strong interactions as well as search for new physics in the tau charm region. As you can see in the innermost part of the detector is midriff chamber. It consists of 14 layers with more than 6,000 sensors. There are 8 field wires around each sense wire, which compose a cell as a square. Its main function is to provide momentum measurement and energy deposition measurement for charged particles. The resolution of energy deposition is 6%, and the momentum resolution is 0.5 at 1 GeV. There are several check packages used in offline check reconstruction at BESIII. Some of them are local check founders like pattern recognition, which firstly search check segments in super layers, then link them to checks, and also have a global check founder based on half transform and use it as a super alignment at a low low PT region. But for low PT checks is still a challenge for them. Many studies show that GNN has a great potential to boost tracking efficiency, especially for low PT checks. So we want to explore the advantage of GNN. Here I use an example to briefly introduce how it works. As the input of GNN graph is composed of nodes and edges. Let's assume this is our input graph. We see that there is one pink node and with pink state. To update the node state, we collect the information of the direct neighbors, which means we perform the message passing. What we end up with is the information about our current node states and the information about our neighbors' node states. Then we perform aggregation to combine their information. Finally, we get a new state or embedding in the next year. As you can see, the pink node only holds information about the blue nodes and itself. But when we perform several of those messaging steps, which corresponds to the neighbors, the neighbor of layers in GNN, this will change. Eventually, in our example, every single node in the graph knows something about all other nodes. We can use the embedding to perform predictions as they contain all the information about the graph that we need. And this is the basic idea of GNN. We learn those embedding by rotatively combine the node information in a local neighborhood. GNN provides node level, edge level, and graph level predictions, and we use H classification GNN. This is a rough workflow of our check method based on GNN. We firstly studied the method of graph construction based on height pattern map, which is a set of all possible neighbor compositions built with Monte Carlo data. so we can know how to assign edges to the haze left by the detector. Then we train the GNN to distinguish true haze on the right from fake haze. Then we try several preliminary methods to build the check conditions. Finally, we use the selected haze on the check to fit the check parameters. When constructing a graph, it's unrealistic to assign edges to any two nodes in the data because most of those edges are fake, and there will make the graph too large and consume too much computing resources. To address this problem, we have established a so-called pattern map based on Monte Carlo simulation. The pattern map contains a set of possible neighbors for each sense ware, and only the haze on the two sense wares of the neighbors will assign an edge. In some other works, people try to define neighbors by calculating the geometry structure in order to truly reflect the characters of the BESIII detector. We use a large number of Monte Carlo data to find all possible neighbors. For neighbors on the similar, we simply define them as two adjacent sense wares on left and right. And for neighbors on the next layer, like what shows in the picture, when the check pass through ware A and then pass through B, B is neighbor, similarly to C. The samples come from single checks Monte Carlo truth information, including 10 cancer particles that can be detected by the main-drift chamber. And when we're using the map, it can be reduced according to the probability of the neighbors, which can further reduce the size of the graph. With the pattern map, we can then transform training data and test data into graphs. We currently use a single simulated check mixed with BESIII random trigger data as background, which include about 14.5% of fake haze. The momentum range is between 0.2 and 3 GeV, and when assigning edges, we connect neighbors on the same layer and neighbors on the adjacent layer mentioned in pattern map. And if they're like this, if there are empty layers in data, we will try to connect the neighbors as well in order not to turn cut the kit, turn cut the check. The node features we select the most original information collected from the main-drift chamber, including the roll drift time, as well as the coordinates of the field sense wares. So the final graph information including node features, adjacency matrix, and edge labels. Overall class feature is very basic structure at present, which including an input network. A graph module consists of node network and edge network, which is repeated for 8 times, and the edge network gives the final prediction score. 10H is used as an activation function. When we use 0.7 as a classification threshold, it has high accuracy for a single check, can reach about 99.5%. The last step is to build checks. For single checks, when tried we tried two methods. The first one is build the longest track. First, remove the edges below the threshold, and then connect the remaining edges to find a condition for the longest track, like the yellow arrow. The second one is we ignore the threshold and take the probability given by the model as a reference. If there is only one edge between two layers, we return it. And if there is more than one edge, we choose the one with the greatest probability, just like the yellow line in the finger. Based on the above method, we get some preliminary result. Here is heat selection efficiency and purity. The definition of the heat selection efficiency is selected true heat divided by the total true heat, and the purity is selected true heat divided by total selected heat. The test data set, as I have already mentioned, is the same as the training data, which have momentum range between 0.2 to 3 GeV. From the two fingers, we can see that GNN gives out both high efficiency and purity. We also further looked into the efficiency of the track funding model by defining 3 matching degrees. The perfect matching means the chosen heads contain all the true heads from the tracks, while the tight and loose match mean containing 75% and 15% of the true heads respectively. This figure on the left shows the performance of the maximum probability method, and the dots of 3 different colors shows the performance of different matching degrees. Well, the performance of the stress determination method is shown on the finger on the left, on the right, which is much better. Furthermore, to evaluate the tracking performance, we also fitted the heads that found by the model for calculate PT. The tracking fitting toolkit GenFit is used to reconstruct the particle PT. The finger on the left shows the fitting efficiency, which means the fitting success rate. As you can see, the fitting success rate remains high even at low PT, which indicates that track connection is good. The PT resolution and the function of particle energy is shown on the right finger, which also looks good. To summarize, we built a track funding algorithm prototype based on H classification GNN at BESIII. It contains a graph construction algorithm based on heat pattern map, a GN module, and several track building methods. Preliminary result BESIII Monte Carlo data shows promising performance, but the results are preliminary, and we still have a lot of optimization work to do. This including optimizing the graph construction method, as well as the GN module to boost performance for low PT tracks, and also finding the worst track building algorithm for multi-track. We plan to cluster with DBSIN or other unsupervised learning method in the future. That's all. Thank you.
Anyone?
Yeah, I had a general comment. So, yeah, this is Liv, by the way. So kind of watching this, I was thinking that there's so many things we're doing with graph neural that are quite similar. And it's such a nice opportunity that we're all here. So I was thinking maybe it would be useful to actually have a GitHub organization or something like that, where everyone could put their code, so we could have it all in one place, and we could kind of gather some resources there, maybe create a Matmos channel as well. If that's something people are interested in, I'd be happy to kind of admin that a bit.
Yes.
Yeah.
More admin sharing. Yes.
but we do. That was actually Savannah's idea 2 years ago. You remember when you were calling in the Xetrax meeting, you said we should. I think you Daniel back there. You are the one who is there is this HSF tracking repository on GitHub where we could put stuff.
Yeah. I mean, I have this ambition, but of course, the bigger their ambition is, the harder it is to implement. And so, unfortunately, at the moment, it's very ambitious and a bit messy and not good enough for like public consumption, probably, if I'm being honest. But we are working on it right now, at least for.
But I think Liv offered to
Yeah, it sounds like we really did offer to help. So that's intriguing. Yeah.
Is it just for tracking? For graph neural nets for tracking? Yeah.
It's right. The idea is tracking. I mean, it'd be nice if it was experiment agnostic.
Yeah.
And a lot of the models are, like, as we're seeing, use the same model again and again, same pipeline again and again. Okay, there's choices about, you know, plug in different constructions or whatever. But yeah, I totally agree. I think this is the right way to go. And yeah, if you're interested, I mean, if Savannah wants to centralize who is curious about doing something like this,
but
that would be nice.
It picks up on something that Joe said after the chat tagging talk, where you also have like, you have a model with some abstract features, some training infrastructure, some way to like, you know, it can go further than just be a tracking related.
Yeah, I could, for instance, create a GitHub organization where we have it divided into different sections, like particle tagging and tracking, and have different repositories within those.
Yes, I support this idea.
Yeah, for sure.
Of course, yeah. Actually doing these kind of things is hard, but I think it would be great if we have more. Well, the more people who are invested in it, the more likely something is to actually get done that is useful to people. So yes, I think this is great.
Okay. This was a coffee break, except we're not going to have a coffee break.
You promised 5 minutes.
Okay, so shall we be back at 10, 11:10? So in 7 minutes from now? Sorry, yeah.
Because there is something I was not really on that talk, is the methodology of using real data, random trigger data, to define as a background. But in that sample, you have full of real tracks. So I don't understand exactly why you use that as a background. Why do you mix single particle Monte Carlo with random trigger data?
Sorry, can you repeat it?
So maybe I misunderstood, but I think you define your training sample with, so basically your signal, what you want to target with single particle Monte Carlo sample. And you mix that with some background sample coming from random trigger data, right?
Yes.
But on that background sample, it's full of real tracks. Maybe low momentum tracks, but still maybe those tracks have some features common to your signal Monte Carlo. So how can you be sure that it doesn't prevent your training to recognize nice track, especially at the moment?
Sorry, can I ask Mr. Li for help?
Oh, sorry, I don't quite understand the question. Do you mean why do we mix the random trick data in the training sample?
Yes.
Is that your correction?
Yes.
Yeah, the idea is to just to mimic the real situation of the data, also to test our track building algorithm to see if that's efficient. Yeah, that's the reason why we use the real data from the collected from the BESIII detector. Yeah, the main reason is to test our track building algorithm to see if it's efficient.
But are you not afraid that you will bias your training, because with the real data you cannot define it's all fake edges in the graph, because you cannot say, oh, those hits were coming from a real particle. So,
yeah, because all the edges are tagged as true or fake. So I'm not quite sure if that will contaminate the training data. Yeah, but that's a good point. We might have to try if we use only the clean data without any background to see if that further improves the final performance. I mean, yeah, in the training data you can remove all the backgrounds, and in the test data in the test set you cannot do that. But yeah, I'm not quite sure if that further improves the performance. Yeah, but it definitely is something we can try.
okay, thank you.
All right, let's thank Xiao Chan again, and let's break for 5 minutes.